Hey guys, welcome back. I hope you had a wonderful weekend. So we're going to be looking at lots of things with correlation tables, including what makes roller coasters fun. So we're going to list off a bunch of different attributes of roller coasters to see what would help it rank higher, I suppose, in this roller coaster ratings that they do for roller coasters around the world. So let's go back to our comparing horsepower versus miles per gallon. So whenever we were looking at horsepower and miles per gallon, our explanatory variable, which was the x-axis, was going to be the amount of horsepower that the engine produced, and then the miles per gallon, our response variable, would be the response variable was miles per gallon. So each one of these points here that we see in our scatter plot represents the x and the y in ordered pair of horsepower and miles per gallon. So this one right here, I think it's actually right here, the lowest one had a horsepower rating of 138 with miles per gallon of 35. And then the highest one over here had 320 horsepower with only 21 miles to the gallon. All right, so the reason why we need to standardize our scatter plots and use z-scores is that sometimes scatter plots, they could actually be stretched out. So depending on the axis scale that we use on the x or the y-axis, so over here for weight, we kind of crunch those down. They're really close together. But for height, we really spread it out. And so this distribution here, it doesn't look like there's very much of an association because it's all more or less vertical. So that slope there looks pretty shallow. But you really aren't looking at slope unless we're looking at an actual standardized scatter plot. So slope is not what we're measuring when we're measuring the strength of an association, by the way, because slope is just going to be related to the amount of spread that we have in the weight and the amount of spread that we have in the height. So if we stretch that distribution out, it doesn't look like it has much of a slope anymore. Another way we could do it is we could stretch out the weight, so the x-axis or the y-axis, and then kind of shrink together the heights. And if we did that, now our slope looks much stronger. So we can't measure the strength of a correlation by the steepness of a slope of what we would say a line of best fit is. Instead, we actually have to standardize all these points. So what we're doing when we standardize is we're using z-scores, right? That's what makes us allows us to compare apples to oranges, like z-scores from female tennis athletes to z-scores of male tennis athletes to see who's the most dominant overall, even though they're not playing against each other or something like that. So when we do z-scores, we're doing observation minus the mean divided by the standard deviation. So this is our observation x minus the x bar, which would be the average height. So your observation, so how tall are you along here? So let's say you're 72 inches, minus the mean, which would be the average, whatever that value is, and then divided by the standard deviation. Well, when we divide by the standard deviation here, that's going to be the key to standardizing the scores. That's what allows us to compare two different distributions, even though we might have two different, I don't know what I'm doing, even though we might have two different distributions with two different spreads. If it had a large spread, we'd be dividing by a large number. If we have a small spread, we'd be dividing by a small number. And this will give us two z-scores, which are unitless. And z-scores, they are unitless. So when we calculate correlation coefficient, it's also going to be unitless. And this is what kind of fixes this issue of kind of spreading out by different axes, or just some tricks that you could do to make it look like there was more of a correlation than there wasn't. So anyway, we always have to standardize the scores because that corrects for small or large standard deviations in two different distributions based on their variables. All right, so if you remember, we calculated the correlation coefficient. I split it out into a separate video. Hopefully you guys will watch it. It was kind of fun, but we found the z-scores for horsepower by doing the list 1 minus the mean, which was this value here, divided by the standard deviation, which is this value, and then that filled in list 3. Same thing with list 4. We did list 2 miles per gallon, the observation, minus the mean, which was given by the two variable stats, or one variable stats, either way, divided by standard deviation, which gave us list 4. Then we took the product of the z-scores, which was list 3 times list 4, that filled out list 5, and then we took the sum of those using the ops menu from math, I think, so math operations, or second list arrowed over to operations. I think that was it. Anyway, we used the sum of list 5, and then we divided by the n-1, which was 14, because there was 15 in each data set. So divide by 14, which gave us our correlation coefficient, which is here. And that's how the calculator does it. It's kind of fun. All right, so here we have it graphed out. These are now standardized. Okay, so these are z-scores for horsepower and z-scores for miles per gallon. I think I know where that one was over there now. Anyway, so z-scores for miles per gallon and z-scores for horsepower. I'll probably put this up here because it makes more sense there. Now, what changed when we did that? So if we have the actual data, here's the actual data in green here. I'll line it up. You can see not much actually changed. Most of the points are pretty much exactly the same, except whenever we did Z-scores, it actually kind of spread out the data for the miles per gallon because it had a slightly larger standard deviation than what the original scatter plot showed. Anyway, so it's very similar. You can also see the difference between the values here. On the top, you have the actual raw values from the scatter plot, and the bottom, you have the Z-scores that represent those values. So anyway, it's going to graph pretty well the same, except it will correct for any crazy stuff that we have there. All right, then when we take the sum of the product of those Z-scores, anything that's on the line, which would have what we'd say in this case average horsepower or horsepower average miles per gallon, when the miles per gallon was 0 in that case, that would mean that it would, when we multiply by 0, it's not going to be negative or positive, so it's not going to affect the strength of or at least the direction of the correlation, but it will affect the strength if we have too many that are typical. So anyway, because those values are still counted. And then all of these that are in the second quadrant and the fourth quadrant would be negative, because you would have negative value for the Z-score here and negative value for the X on the Z-score over here. And so those, when we take the products of those Z-scores, they would be negative. So the sum of all the negative ones here in red, and then the blue ones, which would be 0, so they would be kind of neutral. That would give us our correlation, which is why it was so strong, because they were all pretty well lined up in these quadrants, and there were only a few of them that were typical or average miles per gallon. All right, so there are 3 conditions we have to check before calculating the correlation coefficient. We can't just put two into the calculator, 2 variables in the calculator, and boom, call it good. The first one, we have to make sure that we're dealing with quantitative data. So yeah, that's kind of fun. So quantitative data means we can't calculate the correlation between eye color and IQ or something like that, because where would you place green eyes? Are green eyes before brown eyes, or before blue or hazel or anything? We have no idea, right? You can't calculate favorite color and the length of hair. I mean, that would make no sense. Where would you put the colors in order, like in a bar chart? It wouldn't make sense, because there's no natural order for them or anything like that, unless you're doing like Roy G. Biv or something. I don't know. So then L conditions. Oh yeah, we have to make sure that's linear. So always graph the scatter plot to make sure it's linear in the first place, because if it's a curved association like a parabola, it's going to be close to 0, even though that's not really measuring the strength, because the correlation coefficient only measures the strength of a linear association. And then the other one is outliers. So we have to make sure we don't have any outliers, because those can either ruin or artificially inflate the correlation coefficient, making us think that the correlation is stronger, or the association is stronger than we would originally get. So why are parabolic associations close to 0? Well, this is kind of a nice graphic that I made for you. So if we look at the product of the Z-scores here, this blue point here is not an actual point. It was just kind of representing the mean point. So the mean point is the average x-axis and the average for the y variable as well. So this is the average and the average here. Okay, so that's the mean point is what we call that. That'll be important when we're doing linear regressions, which we're not doing until the next chapter. So don't worry about that, which is like lines of best fit. It's obviously where this is going. So all these positive green ones here with positive X and Y Z-scores are going to be canceled out by the negative ones over here. And all the positive ones in the third quadrant here are going to be canceled out by the negative ones in the fourth quadrant. So what we're left with when we take the sum of the product of Z-scores is something close to 0. Then we divide that by that. It doesn't really matter. It's still going to be close to 0. So the correlation coefficient does not measure the strength of any association, only linear associations. And that's why you have to check the scatter plot before we graph it. Before we calculate correlation coefficient. All right, so then we get into something called a correlation table. So when we have multiple variables, like in business, and they want to know which 2 variables have the strongest association between the 2. As long as they're linear, then we can do these tables. So we do still have to graph them out, but these tables are really great summaries. So we list our variables that we're interested in. So these are from the Forbes magazine on the 500 largest companies. They took 500 largest companies and then took all their data in these different variables and trying to see which one had the strongest correlation, or in other words, the strongest linear association between the 2. So we have assets number, which I guess is like how much the company owns, like in property or whatever. Sales, I'm not really a business person, so might be wrong on some of these, so don't be mad. Sales is obviously how much sales. The market value, so I'm guessing at that current time or how much their stocks are worth in the market. I don't know. Profits, so how much positive money net money that they brought in. So after subtracting their overhead and debt. And then cash flow, which is just how much money is going through the business with the positives and the negatives, and then the number of employees. So these are all their variables. And notice we list the exact same variables in the same order along the x-axis. And then what we have here in the correlation table is we have kind of it's a contingency table, but with correlation. Okay, so what's the correlation between assets and assets? Well, that's going to be 1. Because of course, if you're measuring assets against assets, there's going to be a direct relationship between the two because they're the exact same thing. In this case, same thing with sales and sales. And as you can see, all of these that go along the diagonal are going to have a correlation of 1. So they always show those just so you can kind of see, kind of use it as a reference point, but it's not really any great information because of course, the more market value you have, the more market value you have. You see, the more sales you have, the more sales you have. You see how it's trivial? It's not even that good of information. So if you want to read this, so if we want to know what gives us the most assets, we can read down this column here. So assets, which one has the highest correlation between assets and sales, assets and market value, assets and profit, assets and cash flow, or assets and employees. So the one that has the highest, if we want to know correlation between assets, would be assets and sales. So that's how you'd read the table. Same thing with sales here. So sales and market value, by the way, we'd have to go over here for sales and assets because this one's blank because it's the same repeated information. So read over here. So sales and assets, nope. Okay, yeah. See. Yeah, sales and assets is the 0.7, 0.8, 0.89. Okay, so the largest one would be sales and employees. So those two had the highest correlation, and et cetera, et cetera. So that's how you'd read the table. The highest correlation we see between anything is between profits and cash flow, which is kind of funny. So in order to make the most money, you have to bring in the most cash. Wow, who would have thought? Anyway, you could spend all day analyzing those tables, but they're really interesting, and that's what we're doing today. All right, so 3 conditions to check before calculating the R. This is a repeat. Yeah, but a few things that I want to show you. Obviously, it has to be quantitative, so that's nice. It has to be linear, so we do have to check it because if it's not linear, you got problems. And the reason that you have outliers as being an issue here is that if we have this 1 point here, without that point, it would be very, very strong association and very linear. But this one outlier is going to draw the mean it's going to draw it off of the point right here. So it's going to go from here directly to there. It's going to pull it away towards that outlier, right? And remember, the outlier is going to it's going to skew the mean towards it for the X and the Y variable. And that's what you're seeing here. Kind of cool. All right, so now these values are going to be considered negative or positive instead of being negative because they're in the third quadrant. Because if this, I guess if I move the crosshairs here, I can do that better. Okay. Is it going to let me group them? Now, okay, so if it was right here, now they would all be negative, except this 1 point here draws it out towards it. That is so cool. And now this one would be on an average, so it would be neutral. These are positive, which are going to counteract, and including this one over here, which is a really big positive one. The outlier, that's going to have a big value, just like these do, and it's going to counteract some of those there. And so it's going to lower our correlation coefficient. So this one outlier could make it seem like there isn't a strong association when there really is. It was just an outlier. So you got to be really careful. Same thing going on here with the positives and negatives that we've already discussed. All right, so that's it. Only 14 minutes. That's not too bad for a lecture. Today was kind of simple. We talked about a few things in review, but just adding correlation tables, which is kind of fun. The best problem you'll have is number 43 with when we talk about roller coasters. We'll end on that one. So 28, more correlation errors. So before we were talking about so this is like number 27. Your economics instructor assigns your class to investigate factors associated with gross domestic product, GDP of nations, which is basically the amount of goods and services that is produced, monetary value of goods and services that are produced by a nation's working people in 1 year. So that's GDP. All right. Each student examines these different factors such as life expectancy, literacy rate, etc. for few countries and reports on the class. Reports to the class. Apparently, some of your classmates don't understand stats very well. Surprise, surprise. But you know several of the conclusions are incorrect. Explain the mistakes that are made in the statements below. So We're going to skip to 28. 28A, there was a strong correlation of 1.22 between life expectancy and GDP. So what's the problem with having a correlation of 1.22? So we know a correlation can only be between -1 and +1. We can't have a higher correlation than 1. So clearly they calculated something wrong. There's nothing wrong with life expectancy and GDP because both of these are quantitative data, so there's no problems there. The correlation between literacy rate and GDP, again, both of these are quantitative. A rate and a GDP both have units, so we're fine. Was 0.83. This shows the countries this shows that countries wanting to increase their standard of living, which would be like GDP, should invest heavily in education, which would be like literacy rate. So the problem is that just because there's a strong association, and we would consider this a moderately strong association of 0.8, just because there's a moderately strong association between the two does not mean there's a causal relationship. So this is just a general warning. Correlation does not equal causation. There could be lurking variables at play here. And also we don't know if literacy rate drives GDP or if GDP drives literacy rate. We don't know what direction it goes into without a carefully designed experiment. So anyway, be careful with that. 42, second inning in 2010. Perhaps fans, so this is the part 2. The first part was 41. So they wanted to know if attendance is driven by the runs. So if a American League baseball team scores more runs and make it a more exciting game, and so maybe they have more attendance. I don't know. This is part 2 for that, so 42. But what if its fans are just interested in winning? So we graphed off for the 2010 season, the American League baseball teams, the number of wins that each team had and the average home attendance that they had as well. So here's the graph here. Do winning teams generally enjoy greater attendance in their home games? So if we're looking at the association here, does it look like it's positive or negative? It looks positive. So as we increase in the number of wins this season, it looks like those teams have greater home attendance. Describe the association. Well, it seems to be positive. I would say moderate. It's not super strong. There's still a lot of spread going on here, but I would say a moderate. And if I would have to say, this would probably be linear. So a moderately positive linear association, or however you want to word it. Is the attendance more strongly associated with winning or scoring runs? Okay, so that's the next thing that we need to do. Down here it says use the correlation table to answer the following. So is attendance more strongly associated with winning or runs? So look down here. We want to know attendance, which is this one down here, between wins and attendance or runs and attendance. Which one is a stronger correlation? So they're both pretty weak. Correlation of 0.5 is not that impressive. And as you can see here, I mean, it's pretty weak. The one that's the strongest would be between runs and attendance. So just slightly stronger, like very, very, very slightly. So like 5,000 stronger. All right, explain. Well, we just use the correlation table for that. No big deal. How is the correlation table use the correlation? So how strongly associated is scoring more runs associated with winning? So this is kind of funny. Of course, if you score more runs, you're more likely to win. Duh. So if we look at wins and runs, that's going to be 0.919. So surprise, surprise, teams that score more runs tend to win more. Okay. All right, 39. Yeah, so burgers. Fast food is often considered unhealthy because of its high in both fat and sodium, but are the two related? So fat and sodium, here they listed off fat and sodium content, so several brands of burgers. Analyze the association between fat content and sodium. So we're going to put these in the calculator. Go to stat, edit, and I put them in as list 1 and list 2 here. So you can put those in. All right, find the correlation. So to find correlation, we go to stat, arrow over to calculate, and we're going to go down to linear regression, which is, the fourth option. And then I'm going to do second 1 for list 1, and then second 2 for list 2, okay? And then hit calculate. And if you don't get the value of R here, then you need to go into the catalog, which is going to be second 0. Okay, and then arrow all the way down to diagnostics on. Hopefully it doesn't take you too long. Diagnostics on. Okay, and then hit enter and enter again. And now when you rerun the linear regression, you should get the actual correlation coefficient. So if you didn't do that, we did that on the last video, but make sure you have that. Once you do that setting once with diagnostics on, you won't have to do it again unless you reset the RAM. or load a new operating system, which is what I did. Okay, so the correlation between those is 0.199. Okay, so that's pretty low. Also, before we calculate a correlation coefficient, we need to go ahead and graph it out. That's the rule, right? Because it could be a strong association. It's just not linear. It could be curved, right? So, when I graphed it out, it looks like there's really not a lot going on over here as far as linear. This 1 point just seems to be an outlier, but there's a lot of other data that doesn't quite fit a general trend either. So we're not surprised that we have a low correlation between fat and sodium. So believe it or not, that's, at least with this data, that's not a strong association. All right, so 40, burgers number 2. In the previous exercise, you analyzed association between amounts of fat and sodium in fast food hamburgers. What about fat and calories? So fat content and calories, yeah, that's probably going to be pretty strongly tied together. Here's the data for the same burgers. So I already put fat content in list 1. So now I'm going to put calories in list 3. So you can see that I put that here. So I'm going to do a correlation between 1 and 3 now. So I'm going to go to stat, arrow over to calc, 4th option, and then list. So that would be second 3, list 1. Oops. Go to, let's try this again. Second 3. I don't know why that didn't work. Struggle bus is real. Okay. Calculate. There we go. So 0.96. So between fat and calories is going to be 0.96. Not 0.961. I guess I'm using 3 decimals there. And then, which if we graph the scatter plot, that looks right there, by the way. And you can see that's much more strongly associated between those two. So that value of 0.96, it's a very strong association between fat and calories. And then the next thing we want to know is the next part here. It's not, these answers for the next part aren't in the book, by the way. Burgers 3 is not. I just made them up. So what about the values for calories and sodium? So calories and sodium are list 2 and list 3, by the way. So we're going to run a correlation between those two. See if I can hit delete. So I want to do list 2 and list 3. I think I did it earlier. Yeah, list 2 and list 3. I'm that lazy, I know. So that one was only 0.26. So that's not a super strong association. So which variable have the strongest correlation? So if we just look at these here in our, oh yeah, by the way, fill in the correlation table. The strongest association was between fat and calories. And it actually just has to do with the amount of protein, because the more protein they have in it, the more fat that goes along with the protein as well. So that's kind of what you're measuring. All right, so 43, Thrills 2011. Okay, since 1994, the best roller coaster poll, which actually has a website you can go to, has been ranking the world's best roller coasters. In 2011, for some reason this is doing that. Alrighty. In 2011, the Bizarro earned the top steel roller coaster rank for the 6th straight year. The Bizarro is actually the roller coaster I showed you at the beginning, even though you didn't know that. I just had to Google one of them. That's the one I did. All right, here's the data for the top 10 steel roller coasters from this poll. So here's the ranking 1 through 10. There's their names, which I probably can't pronounce some of them, except Millennium Falcon. Heck yeah, that's the one I'm rooting for. Anyway, and here you have the data that we collected from the different variables. So drop, which would be their highest drop from probably their first, the first drop. Unless they have to have another track that, raises them, that whole thing. Duration, which is how long the ride is. So we're trying to see which variable makes it most likely to rank higher. So did people prefer longer rides, a higher drop starting out, the total height, I guess. The height, I think, is different than the drop because, I don't know, this is the biggest drop and this is the highest point. I'm not sure. You'd have to look it up. If you go to the website, I don't remember, I did it last year. All right, the fastest speed vertical angle. So some of these have a vertical angle of 0. I think Captain has a negative vertical angle because the actual drop actually goes down, which would freak me out. Like my gut would be just unhappy with me doing that. Then the total length of the ride, which is going to be associated with the speed and the duration, by the way, in case you're wondering. All right, so there's all the information, good stuff. So we want to find the association between length and duration. So length, I'm going to put that in list 4, and duration, I'm going to put it in list 5, which I've already done, just for the sake of brevity. So list 4, I put duration. List 5, I did length. Now I want to calculate the association between those two, which I think I've already put up here. Yes. Yes. List 4, list 5. Okay, cool. So that's going to be 0.69 is the correlation coefficient. If we want to graph the scatter plot for that, no big deal. We just go to second y equals. Our x-axis, we're going to do list 4, which is the duration. So we're going to do duration versus length. And then list 5 will be our y list. No big deal. Then just hit zoom 9. And that's it. So I've graphed that out for you here. You can just graph a rough scatter plot. It doesn't have to be perfect, okay? All right. What does the scatter plot indicate about length of the track and the duration of the ride? So clearly, the longer the track is, the longer the ride takes. So there's a pretty strong association. The only other variable there would be the actual speed. So if we looked at the relationship between those two, yeah, that would be pretty clear. All right. That's pretty much it for that one. All right, so I went ahead and filled in the rest of that table for you. The textbook does not do that. So this I did last year, but I calculated all those. I put them in the calculator and calculated them all by hand. You're welcome. So fascinating information. So you can use that to answer the other questions and for your viewing pleasure. By the way, which one of these has the highest correlation between rank? Yes, so rank is what we were interested in. So which one has the strongest correlation? It looks like they're all very weak. None of them are greater than a magnitude of 0.2. Maybe the vertical angle. So, but actually, we're looking for a negative value. And the reason we're looking for a negative value is because rank, the smaller would be better, right? And for everything else, you'd be looking for like a higher number for the speed, higher number for vertical angle. So it looks like this is actually opposite of what we wanted. So if you had a vertical angle, that would have a positive increase in the rank. So people did not prefer crazy vertical angles. You know, that gut feeling just told them, I don't like this. But there were other things, I guess, like duration. So again, people didn't enjoy longer rides either. Maybe that's because they were slower rides. That's why the duration was so long. But the strongest one altogether was actually the drop. Okay, so the highest overall drop, which probably also would relate quickly with speed, but not necessarily because of, you know, reasons like friction. All right, I'm done talking. I will see you guys later.